you're only drawing the outermost valence electrons. Valence electrons are just the outermost electrons. You could write it like that. You could write it like that. But this says, hey, I just have one outside electron for hydrogen. If I wanted to draw it for iron right here, how would I do that? I have two electrons in my outermost shell. So iron, I could just do like this. And electrons, they tend to be paired. So you know, if I have, let's say I wanted to take the example of, if this is Sn, this is selenium. Let me do carbon. Carbon, I have 4 electrons in my outermost shell. So carbon, I could write like this. Carbon, I could write like that. Or if I didn't want to pair them, in theory, I could write them like that as well. And now they're ready to react with other things. Now, what does this tell me about, this one has 1 electron in its outermost shell. This one, these blue, these noble gases, and we'll talk a little bit about them in a second. These have 8 electrons in the outermost shell. How does that help me when I'm actually trying to figure out how things react? Well, it turns out that all atoms want to have 8 electrons in their outermost shell. And that number is important, 8. They want to have 8 electrons in their outermost shell. This is the most stable configuration for atoms, or I guess you could say, and to some degree, a better energy state for the atom. And why is it the number 8? Well, that's something to think about. This is just another kind of fundamental number that just pops out of nature. And I've thought a little bit about it. It must be something about the atoms. When on the outermost shell, when you have 8, they resonate well with each other, and they I don't know, and somehow don't get in the way of each other or don't want to push away from each other. I don't know the answer to that. And frankly, if someone could really answer the question of why 8, exactly why 8, maybe they make a good career for themselves in physics or chemistry. But through experimentation, it has been well established that atoms want to have 8 electrons in their outermost shell. So the question is, if you're dealing with something like, let's say you're dealing with potassium, right? Potassium has 1 electron in its outermost shell. And then you have stuff like, let's say you have stuff like chlorine. Chlorine that has 7 electrons in its outermost shell. What do you think is going to happen if you put some potassium in near some chlorine? What's going to happen? Well, what's the easiest way for the chlorine to get to get 8 electrons? Well, it has 7 in its outermost shell. What's the easiest way? Well, it'll want to gain an electron really, really badly. And what's the easiest way for potassium to have 8 electrons in its outermost shell? Well, if it lost that 1 electron, then it will have 8 electrons in its outermost shell, right? Its outermost shell won't be the 4th shell anymore. It'll be the 3rd shell. But it'll have 8 electrons in the 3rd shell. Its configuration will then look like argon if it loses that 1 electron. So it'll be in a kind of a more stable state. So if you put sodium in the presence of chlorine, what's going to happen? This electron wants to jump off of sodium real bad so that sodium can have 8 electrons in its outermost shell, or have an electron configuration like argon. And that electron is going to jump to chlorine, and then chlorine will have 8 electrons in its outermost shell and also have an electron configuration like argon. And so, as you can imagine, these things, this group right here, which are called the alkali metals, and we'll talk probably in the next video why they're called metals. This group here, alkali metals, and they tend to exclude hydrogen, and we'll talk about that. And these really want to give away electrons. And because of that, they're highly, highly reactive, especially if you put them in the presence of these elements, these yellow elements right here, which are called the halogens. These really, really want to take electrons from other things because they just need 1 to get to 8. These really want to give away electrons because they just have to give away 1 to get to 8. And the reason why hydrogen actually isn't included is because hydrogen doesn't want to give away its electron as bad as these guys. Hydrogen, this rule that your outermost shell wants to get to 8, that's true for everything except for hydrogen and helium. Hydrogen and helium, just because they have 1 shell, they're happy with just 2 electrons. And so with hydrogen, sure, it could lose an electron, but could just easily gain an electron and be happy because it'll have a full first shell. But all of these other ones, these alkali metals, they want to give away electrons really bad. And when people in chemistry talk about metallic nature, They're really talking about how badly something wants to give away electrons. Anyway, I'm all out of time now. In the next video, we'll continue discussing the groups in the periodic tables and any trends we can ascertain from